Welcome to GATE class. So in this class we will just discuss then some of the important properties of Fourier transform. So let us discuss the time shifting property. Let us discuss the time shifting property. Time shifting property. So according to this property, if GT has this Fourier transform GF, then GT minus T naught should have Fourier transform of GF exponential minus J 2 pi F T naught. And so of course this property is basically we have delay in times. Here we have delay in time, and it depends on the value of T naught whether the GT will shift to positive direction or negative direction. All these things will depend on the value of T naught. So what is T naught? So where T naught is a real constant, where T naught is a real constant time shift, where T naught is real constant time shift. So we can prove this property. Very easily. What is that Fourier transform of GT minus T naught? So the Fourier transform of GT minus T naught is equal to minus infinity to plus infinity GT minus T naught exponential minus J 2 pi ft dt. So this is basically the Fourier transform. This is the definition of Fourier transform. So let T minus T naught is equal to K, then dt will be equal to dk, and the limit will change from k is equal to minus infinity to k is equal to plus infinity gk exponential minus j 2 pi f k plus T naught into dk. So what we are getting here, we can put e raised to the power minus j 2 pi f T naught outside, because it is independent of that, not a function of k. So it is e raised to the power minus j 2 pi f T naught we can put outside, and the remaining terms we can put so it is minus infinity to plus infinity gk e raised to the power minus j 2 pi fk into dk. Now this is again, if we see carefully, this is the Fourier transform of gf. So it is minus j 2 pi f T naught multiplied by gf. So GT minus T naught has Fourier transform. So the Fourier transform of GT minus T naught is equal to e raised to the power minus j 2 pi f T naught into GF. So this is the Fourier transform of GT minus T naught. Now what is that important thing about this property? So basically this time shifting property, if we carefully observe that the time shifting property states that if a function GT is shifted along the axis along the axis by an amount T naught, the effect is equivalent. The effect is equivalent The effect is equivalent to multiplying its Fourier transform GF to multiplying its Fourier transform GF by the factor exponential minus j 2 pi f t naught, exponential minus j 2 pi f t naught. This means that amplitude of GF is unaffected by the time shift, but its phase, please understand, but its phase is changed by the linear factor minus j 2 pi f t naught. So please understand that this g dash f is exponential minus j 2 pi f t naught into gf. So basically we just find out the amplitude, so it will remain same because the magnitude of this it will be equals to modulus of GF only. So the magnitude, basically the amplitude will remain same. The amplitude spectrum will remain same, but problem is that the phase is changed by a linear factor of minus 2 pi f t naught. The phase will change by a linear factor of minus 2 pi f t naught. So this is a very important property, and this property is called the time shifting. Now we have another important property that is called frequency shifting property. So according to this property, if GT has Fourier transform GF, then if multiply GT with exponential j 2 pi fct, then what we will get? The Fourier transform is equals to GF minus FC. The Fourier transform is equals to GF minus FC. So what is FC? So where FC is a real constant frequency, is a real constant, where FC is a real constant frequency, and we can prove this, so there is a proof given below. So we have GT. So if we find out GT, that Fourier transform of e raised to the power j 2 pi fct into GT, so that is equals to minus infinity to plus infinity e raised to the power j 2 pi fct into GT e raised to the power minus j 2 pi fct into dt, and that we can write it as minus infinity to plus infinity GT e raised to the power minus j 2 pi. We can write it as here we have this ft. This is ft minus j 2 pi, because we have already taken fc here, so we need to take f here, so it is f only. So it is f minus fc into t into dt. So it is simply it is that if we just see that carefully, then it is nothing but that gf minus fc. So the Fourier transform of e raised to the power j 2 pi fct into gt is equals to gf minus fc. So what is that conclusion for that property? What is the important point for this property? So this is basically if we see that there is a multiplication, so that is the multiplication, that is the multiplication of a function, that is the multiplication of a function gt by a factor e raised to the power j 2 pi fct is equivalent to shifting its Fourier transform, is equivalent to shifting its Fourier transform GF along the frequency axis, by the amount fc, So this property is a special case. This property is a special case. This property is a special case of the modulation theorem. Special case of the modulation theorem. So basically a shift of the range, of frequencies, of the range of frequencies in a signal accomplished by using the process of modulation. So all these things let me clear to you. Let me give you an example. So where we are going to use this frequency shifting. So we have radio frequency pulse, like we have amplitude modulated wave. So let us discuss the same wave. So in this let us discuss that DSB. Let us discuss DSB-SC. So DSB-SC wave is simply we have message signal multiplied by carrier signal. So message signal is AM cos 2 pi FMT and carrier signal is simply AC e raised to the power j 2 pi FCT plus e raised to the power minus j 2 pi fct divided by 2. So basically the carrier signal is, please understand, the carrier signal is AC cos 2 pi fct. So we have written it as AC by 2 e raised to the power j 2 pi fct plus e raised to the power minus j 2 pi fct. So what is happening that we have AM AC divided by 2 e raised to the power j 2 pi fct cos 2 pi fmt plus AC AM divided by 2 e raised to the power minus j 2 pi fct cos 2 pi fmt. Now we need to find, if we find out the spectrum of this signal, then spectrum is, let it is SF, the Fourier transform of ST is SF, and the Fourier transform of this signal, we can apply that shift in frequency. So what is Fourier transform of? So what is Fourier transform of? Please, if you maybe some of you don't know the Fourier transform of cos 2 pi fct. So the Fourier transform of cos 2 pi fct is 1 by 2 del f minus fc plus del f plus fc. So this is the Fourier transform of cos 2 pi fct. Now basically cos 2 pi, instead of cos 2 pi fct, we it is good to take fm, because our reference signal is fm. We are going to find out that Fourier transform of cos 2 pi fmt. So it is 2 pi fmt. So it is del f minus fm plus del f plus fm. So this is the Fourier transform of cos 2 pi fmt. Now what is going on here? We are just providing multiplication of this signal with that signal cos 2 pi fmt. So the frequency shifting will take place. So it is equals to am by ac divided by 2, and basically what we are getting here, we are getting 1 by 2 del f minus, so what we are getting here, this frequency, this is shifted at fc, and this is shifted at minus fc. So what we are getting here, so better to write in next slide, all these things better to write in next slide. So the DSB-SC wave, we have discussed the DSB-SC wave. So we have ST, that is equals to MT multiplied by CT, and it is equals to AM cos 2 pi FMT multiplied by cos 2 pi FCT. So what is here? We have AM and here AC also. So AM into AC cos 2 pi FMT, and cos 2 pi FCT we can write it as e raised to the power j 2 pi FCT plus e raised to the power minus j 2 pi FCT. So what we will get here? We will get AM by AC divided by 2 e raised to the power j 2 pi EFCT multiplied by cos 2 pi FMT plus AC into AM divided by 2 e raised to the power minus j 2 pi FCT cos 2 pi into FMT. Now what is Fourier transform of cos 2 pi FMT? So the Fourier transform of cos 2 pi FMT is equals to 1 by 2 del f minus fm plus del f plus fm. So if we draw the frequency spectrum, then we have a delta function of at fm, and we have another delta function at minus fm. So it is 1 by 2 del f minus fm, and here the delta function 1 by 2 del f plus fm. So these two delta functions are present. Now we are going to shift this at fc and minus fc. So what we will get here, because here we are getting plus j 2 pi ct, and here we are getting minus j 2 pi fct. So where the shifting will take place? So where the shifting will take place? So we can apply the frequency shifting property. And what frequency shifting property is saying that since because we have multiplied here by e raised to the power j 2 pi fct, so what we are getting here, this will shift to fm, this all these things will shift to minus fc, and here we have multiplication of minus j 2 pi fct, so all these things will shift to plus fc in this case and minus fc in other case. So let us draw the spectrum. So let us first we can write that Fourier transform. First we can write the Fourier transform. So we have two signals here, so this is first signal and this is second signal. So let us solve this, let us find out the Fourier spectrum, that frequency spectrum. So we have st that is equals to s1t plus s2t. So here s1t is equals to am ac by 2 e raised to the power j 2 pi fct cos 2 pi fmt. So S1f is Fourier transform of this signal. S1f is Fourier transform of am ac by 2 e raised to the power j 2 pi fct cos 2 pi fm into t. So let us find out the Fourier transform of this term. So let us find out the Fourier transform of that term. So we have the Fourier transform of cos 2 pi fmt. So it is two frequency present at, one frequency is present at fm, another frequency is present at minus fm. So this is Fourier transform of cos 2 pi fmt, that is equals to 1 by 2 del f minus fm plus 1 by 2 del f plus fm. So here we have 1 by 2 del f minus fm, and here we have del f plus fm. Now we need to find out the Fourier transform of am by ac. If we see the previous slide, so what we need to find out? We need to find out the Fourier transform of am ac divided by 2. Please wait. So we need to find out the Fourier transform of am ac divided by 2 e raised to the power j 2 pi fct multiplied by cos 2 pi fmt. So here we are going to apply the multiplication of this factor. So what we will get? We will get the frequency shift. The frequency will shift at fc. So entire frequency will shift at fc. So the spectrum of S1f, please understand, so the spectrum of S1f is very simple. We have to just the shift. So this 0 will shift at fc, this fm will shift at fc plus fm, this minus fm will shift at fc minus fm, and because fc is very greater than fm, so we are taking very higher range for this fc. Now there are two delta function, one is present at fc minus fm and another one is present at fc plus fm. So we have two delta functions. So this is your 1 by 2 del. So this is shifted at fc. So we have 1 by 2 del f minus fc plus fm, and another delta function is 1 divided by 2 del f minus fc minus fm. So this is our delta function. This is our delta function. So in the similar way, we have the spectrum of S2F. So what is the spectrum of S2F? So the spectrum of S2F is that we have two delta functions of strength AC AM divided by 2 del. So one is shifted at, basically this 0 is shifted at minus Fc. This Fm is shifted at minus Fm plus Fc. That original signal we have, this is Fm, this is minus Fm, so it is shifted at minus Fc. 0 is shifted at minus Fc. This is minus Fc minus Fm. This is minus Fc plus Fm, and here we have AC AM by 2 del F minus Fc plus Fm, and here we have F minus Fc minus Fm. So finally that spectrum of SF. So spectrum of SF is, we have two delta function here in positive direction, also we have two delta function present in negative direction. So it is Fc minus Fm, it is Fc minus Fm, it is Fc plus Fm, it is minus Fc plus Fm, and minus Fc minus Fm. So it is the spectrum of SF. It is the spectrum of SF. So ultimately we have used that shifting property. So this is called, that's why it is very useful in case of modulation, because our low pass signal, basically we have Fm and minus Fm, that frequency, basically we are shifting it to Fc and minus Fc. We are shifting it to Fc. So this basically we are doing the superposition. So this is very simple example of how we are going to do the superposition, and this frequency shifting concept is used in modulation. So this frequency shifting concept is used in modulation. So every modulation, if you say that AM, FM, and that digital modulation technique, so all these modulation techniques, any modulation technique, we have the basic requirement is that we have a message signal, and we have a carrier signal. The basic requirement is that we have a message signal and we have a carrier signal, and the carrier signal frequency Fc is very very high as compared to the message signal frequency. So this is our frequency spectrum of SF, that is DSP-SC modulated wave, the frequency Fourier transform of DSP-SC modulated wave. Let us take another example. That example is basically related to radio frequency pulse. Radio frequency pulse, and that is simply we are calling RF pulse. So let us do that. Let us see what is happening here. So consider the pulse signal GT. So we have a pulse signal GT given below. This is GT. So this is a pulse. Consider a radio frequency pulse. So we are not taking entire sinusoidal signal, only we are taking some part of that. That's why we are calling it as pulse. So this is a radio frequency pulse. Forgive me, my drawing is not good. So we are considering only for capital time t. So we have +1 and -1. That higher amplitude is +1, lower amplitude is -1, and the frequency is fc. So this is time period, and the frequency is 1 divided by fc. So the frequency is the time period is 1 divided by fc, and fc is the frequency of this pulse. Fc is the frequency of this RF pulse. Now we are going to apply the frequency shift that we have used. So basically this RF consists of, so this consider that pulse signal GT given below that we have shown in previous slide. So it consists of that RF pulse consists of a sinusoidal wave of unit amplitude. So it is shown in the previous figure that we have taken the amplitude unit, that is ±1, and that frequency we have taken, and the frequency is fc. So the frequency is fc. Fc is the carrier frequency, pulse frequency. So and also it is extending in duration from -t/2 to +t/2. So the duration of the pulse is capital T. So it goes from -t/2 to +t/2. So it goes from -t/2 to +t/2. So the signal is sometimes referred to as RF pulse. So the signal is sometimes referred to as RF pulse. So the signal is sometimes referred to as RF pulse when the frequency fc falls in the radio frequency band. When the frequency, it is sometimes referred to as RF pulse when the frequency fc falls in the radio frequency band, So the signal GT may be expressed mathematically. So the signal GT may be expressed mathematically as GT is equals to rect T divided by capital T cos 2 pi fc into T. So this GT is basically rect T divided by capital T cos 2 pi fc into T. So to find the Fourier transform, of the RF signal, to find the Fourier transform of the RF signal, we first use Euler's formula to write. We first use the Euler's formula. That Euler's formula is equals to, so what is Euler's formula? So it is cos 2 pi fct, that we can write it as 1 by 2 e raised to the power j 2 pi fct plus e raised to the power minus j 2 pi fct. So this is Euler's formula. So how to write gt? So gt we can write it as, if we see that if we see carefully, then we can write gt as 1 by 2 uh, rect t divided by t multiplied by e raised to the power j 2 pi fct plus e raised to the power minus j 2 pi fct. So what is happening here? Let me explain this. So this is our pulse. So this is our pulse, and the duration of pulse is capital T. So this is the duration of pulse, and the frequency is 1 fc. So it is 1 divided by fc. So and that amplitude is plus minus 1. So this amplitude is plus minus 1 and fc is the frequency. So this is our pulse. Now what we are going to do, we are just multiplying this pulse with this rectangular box of duration plus minus t and amplitude is 1. So this is rect t divided by capital T, because amplitude is 1. So what we are going to do, so if we multiply this rect with this cosine, if we multiply this rect with this cosine wave, so this is cosine wave. So if we multiply this rect with cosine wave, then it will acquire only the width, the common area. This common area is between the width of this rectangular box only. So what we are going to do, we have just contained that pulse. We have just taken the pulse that width has only t. We have just taken the t width pulse. Because we have multiplied with a rectangular window. This is simply a windowing technique. So we have just multiplying this with rectangular. So if this rectangular pulse, this rectangular window is multiplied with this cosine wave, then we will get this type of pulses. We are getting this type of pulses. So we have written in this way. Now we can easily find out the Fourier transform. So how to find out the Fourier transform? So if we just carefully see that, then the Fourier transform of a rect t by t is at sin ft. If a is equals to 1, then the Fourier transform of rect t by t is t sin ft. This is the Fourier transform of this rect function. Now what we are going to do, we have just we can apply the frequency shifting property. So if we multiply this rect with e raised to the power j 2 pi fct, if we multiply with this rect with e raised to the power j 2 pi fct, and if we find out the Fourier transform, then it is equals to t f minus fc. It is very simple. So we have it is equals to t by 2 sin t f minus fc plus sin t f plus fc. So we are getting this type of signal. So this is gf, and this is simply the multiplication of, this is gf, and this is simply the multiplication of this so basically this is frequency shifting operation. So, and when we have multiplied with So it is half here, and when we have multiplied half e raised to the power j2 minus 2 pi fct with rect t by t, so what we will get? We will get t by 2 sinc t f plus fc. So we are getting this. Now if we sum these two, so if we sum these two, then the Fourier transform of gt, the Fourier transform of gt is given as t by 2 sinc t f minus fc plus sinc t f plus fc. So this is the Fourier transform of gt. So in this way, what we have done, let me explain with the spectrum. Let me explain with the spectrum. So this is the spectrum of the pulse. This is the spectrum of the pulse. So this is width of pulse, and this is +1, this is -1. Now we have shifted the spectrum at fc and minus fc. So we have shifted the spectrum. This is amplitude spectrum. We have shifted at plus fc and minus fc. So this is the amplitude spectrum, and it is shifted at plus fc and minus fc. It is t by 2 because sinc function is there. Two sinc function is there. One sinc function is present at, so this sinc function, this sinc function is present at EFC. So this sinc function is present at FC, and there is another sinc function. So this sinc function is present at minus fc. So we have two sinc functions, and basically we have taken the modulus here. That's why the negative lobes of this sinc function becomes positive, because we have taken the modulus here. So every negative area will become the positive area. And of course the sinc function is basically the decreasing type, but it is an energy signal. Why it is an energy signal? Because it is bounded. When we have t tends to infinity, when we have f tends to infinity, it is 0. It is 0. That's why this is the sinc function is basically energy signal. So sinc function is an example of energy signal. So sinc function is an example of sinc function is an example of energy signal. So let us discuss another very important property. So that property is area under GT. Area under GT. So according to this property, if GT has the Fourier transform GF, if GT has the Fourier transform GF, then if we integrate GT from minus infinity to plus infinity, then it is equal to Z0. So it is very simple to prove that. So let us prove this. So GF is equal to minus infinity to plus infinity GT e raised to the power minus j 2 pi ft into dt. Now put f is equal to 0, so we will get Z0 is equal to minus infinity to plus infinity GT, and that is equal to minus infinity to plus infinity GT dt. So what is the conclusion? Minus infinity to plus infinity GT dt is equal to G0. So this is area under this. So area of this GT is equal to G0. So it is very interesting. If we have a frequency spectrum, then if frequency is equals to 0, if we put the frequency is equals to 0, then the value of that frequency spectrum at f is equals to 0 is nothing but it is equals to the total area acquired by the signal gt. It is nothing but the total acquired signal area acquired by the signal gt. So this is so that is area under a function gt is equals to the value of its Fourier transform gf at f is equals to 0. So we can say that, so that is, we can write it as, that is the area under a function gt, under a function gt, the area under a function gt is equal to the value of its Fourier transform gf, of its Fourier transform gf at f is equals to 0 is equals to the Fourier transform gf at f is equals to 0. Now discuss another important property, that is area under gf. So in last property we have discussed the area under gt. Here in this property we are going to discuss the area under gf. So if gt has Fourier transform gf, if gt has Fourier transform gf, then g0 is equals to minus infinity to plus infinity gf df. So area under this gf is z0. So it is easy to prove that, because gt is minus infinity to plus infinity gf e raised to the power j 2 pi ft into df. Now if we put f is equals to 0, what we will get, if we put t is equals to 0, what we will get g0 is equals to minus infinity to plus infinity gf df. So this is area, so this is simply the area, g0 is simply the area of gf, g0 is simply the area of gf. So that is the value of function gt at t is equals to 0 is equals to the area under the Fourier transform. So what we can say that the area under the Fourier transform, the area under the Fourier transform is equal to the area the area under the Fourier transform is equals to the value of function gt is equals to the value of function gt at t is equals to 0. So if we put t is equals to 0, then we will calculate the area, that is the area of gf. Now let us discuss another important property. That property is called the differentiation in the time domain. That property is called the differentiation in the time domain. So let gt has the Fourier transform gf, and assume that the first derivative of gt with respect to t is Fourier transformable, transformable, then d by dt of gt is equals to the Fourier transform is equals to j 2 pi f into gf. So d by dt of gt, the Fourier transform is j 2 pi f into gf. So that is differentiation of a time function gt, that is differentiation of a time function, that is differentiation of a time function gt has the effect of multiplying its Fourier transform gf by the purely imaginary factor j 2 pi f, by the purely imaginary factor. So dn gt divided by dtn, if we find out the Fourier transform, that is equals to j 2 pi f raised to the power n into gf. Let us discuss another property, that is integration in the time domain. So this is very important property, and it says that if gt has Fourier transform gf, and it is provided that this g0 is equals to 0, so we have minus infinity to t g tau d tau is equals to 1 divided by j 2 pi f gf. So that is the integration of a time function, that is integration of a time function gt has the effect of dividing its Fourier transform gf by the factor j 2 pi f, provided that g0 is equal to 0, so 0. If this condition is provided, then minus infinity to t g tau d tau is equal to 1 divided by j 2 pi f into gf. So another important property is modulation theorem. Modulation theorem. So if we have Fourier transform, if gt has Fourier transform gf, let g1t has Fourier transform g1f, and g2t has Fourier transform g2f, then g1t multiplication of g2t, the Fourier transform is equals to minus infinity to plus infinity g1 lambda g2 f minus lambda d lambda. So we conclude that, so what we can, so we conclude that the multiplication of two signals, the multiplication of two signals, so we conclude that the multiplication of two signals in the time domain is transformed into the convolution of their individual Fourier transform of their individual Fourier transform in the frequency domain, So this property is known as modulation theorem. So this property is known as modulation. This property is known as modulation theorem. This property is known as modulation theorem. This property is known as modulation theorem. So what we are going to see that if we have G1t modulation with G1t multiplication of G2t, so G1t multiplication with G2t, the Fourier transform is G1f convolution with G2f, and that is also equals to G2f convolution with G1f. That is same. So this multiplication, so very important thing is that multiplication in time domain is equals to convolution in frequency domain. So multiplication in time domain is equals to convolution in frequency domain. This is very important property. This is called the modulation theorem. Next thing is the convolution theorem. Next property is convolution theorem. So according to this theorem, let GT has Fourier transform GF. Let G1T has Fourier transform G1F, and G2T has Fourier transform G2F. Then minus infinity to plus infinity G1 tau, G2T minus tau d tau. If we find out the Fourier transform, then it is equals to G1f multiplied by G2f. So we can say that, so basically it states that the convolution of two signals, so it states that the convolution of two signals in the time domain is transformed into the multiplication of their Fourier transform in the frequency domain equal to the is transformed in the multiplication of their Fourier transform in the frequency domain in the frequency domain. So we can observe that when we have multiplication in time domain, then it is equals to convolution in frequency domain, as we have seen in the previous property, that is modulation theorem. So what we have seen in the modulation theorem, that we have two signals, and the multiplication of two signals, if we find out the Fourier transform, then it is basically the convolution in frequency domain. But here in this property, that is called convolution theorem, if we have two signals, then the convolution of two signals in time domain is equals to the multiplication of two signals in frequency domain. So this basically this application we have used during the analysis of our discrete and continuous time LTI system. So if we have system with impulse response ht, and the input is gt and the output is yt, then the yt is equals to gt convolution with eht. This is our definition of LTI system. It is LTI system. This is our definition. Now if we take the Fourier transform on both sides, so that yf is equals to, since it is the convolution in time domain, so we have multiplication in f domain or frequency domain. So we have multiplication in f domain. So this is convolution in time domain, and that is equals to multiplication in frequency domain.